Welcome to our video on extraneous solutions. When solving certain types of equations, particularly those involving radicals or rational expressions, we sometimes encounter solutions that don't actually satisfy the original equation. These are called extraneous solutions. Extraneous solutions are values that appear to be solutions when we follow standard algebraic steps, but when we plug these values back into the original equation, they don't actually work. These solutions often arise when we perform operations like squaring both sides of an equation or multiplying both sides by an expression containing the variable. These operations can introduce new solutions that weren't present in the original problem. Let's look at a simple example to understand how extraneous solutions can occur. Consider the equation square root of x equals -3. Now, what happens if we square both sides? We get x equals 9. Let's check if x equals 9 is actually a solution by substituting it back into the original equation. The square root of 9 equals 3, not -3. So x equals 9 is an extraneous solution. The original equation has no real solutions because the square root of a number cannot be negative. Here are some key points to remember about extraneous solutions. First, they often arise when we perform operations that aren't reversible in a one-to-one manner. Second, we must always verify our solutions by plugging them back into the original equation. And third, the presence of extraneous solutions doesn't mean we made a mistake in our algebra. It's just a natural consequence of certain algebraic operations. Now, let's tackle a more complex problem. Solving the equation square root of x minus 1 equals 2 times square root of x. This equation involves two radicals, and we'll need to isolate one of them to solve it. Let's solve this step by step. First, we square both sides of the equation. This gives us x minus 1 equals 4x. Squaring both sides is a common technique for eliminating radicals. However, this is precisely one of those operations that can introduce extraneous solutions. Now, we solve for x by subtracting 4x from both sides. X minus 1 minus 4x equals 0, combining like terms. -3x minus 1 equals 0, solving for x. -3x equals 1x equals -1/3. Let's visualize this equation and our supposed solution. Here, I've graphed y equals square root of x minus 1 in blue and y equals 2 times square root of x in red. The solution to our equation would be the x value where these two graphs intersect. Let's look at x equals -1/3. Is this an intersection point? Wait, there seems to be a problem. These functions are only defined for certain domains. The blue function requires x minus 1 to be greater than or equal to 0, which means x must be greater than or equal to 1. The red function requires x to be greater than or equal to 0. So neither function is even defined at x equals -1/3. Now, let's formally verify whether x equals -1/3 is actually a solution by substituting it back into the original equation. On the left side, we have square root of x minus 1, which is square root of -1/3 minus 1. That's square root of -4/3, which isn't a real number because we can't take the square root of a negative number. So x equals -1/3 is an extraneous solution. It emerged from our algebraic steps, but it doesn't satisfy the original equation because it's outside the domain of the function. So, what is the actual solution to our equation? Let's look back at our graphical representation. To find the intersection point, we need to find where these two curves meet. They actually intersect at x equals 4. Let's verify this. When x equals 4, the left side is square root of 4 minus 1, which is square root of 3, approximately 1.732. The right side is 2 times square root of 4, which is 2 times 2, or 4. Wait, that's not equal. Let me double check my work. In fact, these curves don't intersect at all within the real number domain. The equation square root of x minus 1 equals 2 square root of x has no solutions. Let's prove algebraically why this equation has no solutions. If x is less than 1, then the left side of our equation, square root of x minus 1, isn't a real number. If x is greater than or equal to 1, then both sides of the equation are defined. Let's compare them. The left side is square root of x minus 1, which is always less than square root of x. The right side is 2 times square root of x, which is always greater than square root of x. Since the left side is always less than square root of x, and the right side is always greater than square root of x, they can never be equal for any value of x. So our equation has no real solutions. In conclusion, this problem illustrates the importance of checking for extraneous solutions. Our algebraic steps led us to x equals negative 1/3, but this was an extraneous solution because it's outside the domain of our original equation. Welcome to our lesson on setting restrictions before solving equations. Today, we'll learn why setting restrictions is crucial when solving certain types of equations and how it helps us avoid extraneous solutions. So, why do we need to set restrictions before solving certain types of equations? When working with expressions like square roots, fractions, or logarithms, not all values of x will make sense in the context of the problem. For example, square roots require the expression inside to be non-negative. Fractions require a non-zero denominator, and logarithms require positive arguments. Setting these restrictions before solving helps us avoid mathematical errors and ensures that our solutions are valid in the original context of the problem. Let's look at our first example, finding the restrictions for the expression square root of x minus 1. For any square root expression, we need the expression under the radical to be greater than or equal to 0. So we set up the inequality x minus 1 is greater than or equal to 0. Solving for x, we add 1 to both sides. X is greater than or equal to 1. Therefore, the domain restriction for square root of x minus 1 is x greater than or equal to 1. This means any value of x less than 1 would make our expression undefined in the real number system. Now, let's solve a complete equation with restrictions. X squared minus 2x divided by x equals 0. First, let's identify the restriction. Since we have x in the denominator, we must have x not equal to 0. Now, let's solve the equation. We can factor the numerator x times. X minus 2 divided by x equals 0. We can simplify by canceling one factor of x from the numerator and denominator, giving us x minus 2 equals 0. This gives us x equals 2. But wait, if we look at the original factored form before canceling, x times x minus 2 equals 0 would give us x equals 0 or x equals 2. Let's check both solutions against our restriction. We said x cannot equal 0 because it's in the denominator. So x equals 0 violates our restriction and isn't a valid solution. Therefore, the only valid solution to the equation is x equals 2. Finally, let's discuss how restrictions relate to extraneous solutions. An extraneous solution is a solution that satisfies the transformed equation after we've manipulated it, but doesn't satisfy the original equation. For instance, in our equation, x squared minus 2x divided by x equals 0, we found that x equals 0 would make the original expression undefined. The cancellation step in solving could introduce extraneous solutions if we don't check our answers against the original restrictions. This is why setting restrictions at the beginning is so important. It helps us identify and eliminate extraneous solutions that might arise during the solving process. To summarize, always identify domain restrictions before solving. Check all potential solutions against these restrictions. Eliminate any solutions that violate the restrictions. The remaining solutions are your valid answers.